to GLOBEBUSTERS.
We accept the reality of the world with which we're presented. It's as simple as that.
All right, hello and welcome, lads and ladettes, to GLOBEBUSTERS Season 13, Episode 11. Today, Zachary Zimbala is going to be giving a presentation on electrostatics, live and in the field from his office. And I'm joined, of course, by Shane St. Pierre. Welcome, Shane. Welcome, Zach.
What's up, lads? What's up, everyone?
How's it going, fellas?
Going great.
Hope everybody's having a good day.
Having a fantastic day. Before we get into the Prezi, I'd like to give a special shout out to Cami for continuing this platform and allowing GLOBEBUSTERS to continue on and to carry on with Bob's legacy. If you'd like to support Cami, you can donate here on YouTube with super chats, and we will read those throughout the episode and touch base with those. And that's how you can support Cami and Bob's legacy. Let's get into it whenever you ready, Zach.
Yeah, so electrostatics. I was never taught anything about electrostatics in any of my science classes. I refused to do physics because it was nothing but a bunch more math, they told me. But they may have gotten into it a little, but even like a lot of college level physics, they'll touch on electrostatics, but they don't actually teach how important it is and how strong of a force it actually is here on Earth, even in the heliocentric model. It totally blows gravity out of the water. Now, people would say, well, that's crazy talk, right? How can you say that, electrostatics is stronger than gravity? And it's not me saying this. This is, MIT physics professor of 4 decades, Walter Lewin. And he explains it very clearly. I would show it to you, but every time I do, we get struck with the copyright. So, we fought him, but pretty much, they have the right. YouTube has the right. This isn't, a platform of free speech. And pretty much they said, yeah, you'd win, but we're going to make you take it to court. And it's not worth all the court costs and all that kind of stuff. And YouTube has, ungodly amounts of money to play in court as long as they want. But yeah, anybody can go watch the video. It's his lecture 1 of his electricity and magnetism, his 802 course that he taught at MIT. He actually put the whole course out on YouTube for free. Amazing course. I've learned so much from this man. Never got to meet him. He's still around, still putting out videos on YouTube. He put one out earlier today. He just loves teaching. He really loves teaching. He's probably the greatest teacher I've ever witnessed because of stuff like that. Like, I bought all of this behind me because of him. All these little toys and gizmos and gadgets. The Wimshurst was actually donated by an awesome gentleman. But yeah, I watched Walter Lewin do all these tests, and I've seen illusions and magic tricks. So instead of just taking his word for it, I went and bought them and then tried it all out myself. And I really learned a lot more than he taught me. When you play with things by yourself and you actually get down and dirty with the actual toys and not just the words on paper and the numbers, you realize that those numbers don't always, this is like a fluid system when it comes to electrostatics. Just as fluid as the air is around you. There's electrostatics moving all over the place, and we're going to show you that here. We're going to start off with what are called electrostatic rods. Now, according to the story, we learned about electrostatics from rubbing amber jewelry on clothing and then touching frogs with it and see them in their adverse reaction to getting shocked with a negative charge, which I can attest to. I've had that wand sitting in my lap a few times. It doesn't feel like a shock, but it's actually almost like sucking the energy out of you. I didn't like the feeling at all. It's not something I won't do it again on purpose. But you know, I'm sitting there for hours playing with the Van de Graaff, and sometimes you just leave the thing sitting in your lap or something, and it's not like a shocking, it's like a sucking. It's weird. It's really, really weird. But this right here, just a rubber rod and some cat fur. I don't know why they use cat fur. They've been doing it for hundreds of years. You go and buy one of these kits, they're going to give you a thing of cat fur. And you just rub it. Well, here, first, I don't know how much charge it has. I'll try to discharge it a little bit here. And can you bring up so people out in the audience can see? Oh, you already got it up. Awesome. That is actually our electric field. This is the EMF meter. And here, I'm going to bring it up so I can see it bigger. So it's bouncing between 70 and 76 volts right now. And that's because it's up off the ground on this table. This EMF meter is right here. If I touch it, it's going to, here, I'll just touch it. We'll see if I can do it without making it spike. There's a little spike there. But now you can see it's going to drop down to 0 because I'm touching the ground. Or real close to 0. Set it back up here. And that's just showing the electric field intensity. And if you notice, it's actually going up and down. It's got a heartbeat to it. And you don't really find that, I haven't found that in any literature yet. This, what we're watching right now, that up and down looking heartbeat of the electric field, they don't really talk about that. They talk about the daily one that happens. Every 24 hours there's a pulse. But I can't, I'm sure it's out there somewhere. So what I'm going to do, I'm just going to rub this rod with this cat fur, and I'm going to put the rod near this voltmeter. Give it a little bit of a charge. And when we set it down here, we should get some reaction. I'm not touching it. I'm just putting it near it. And you can see we got a nice little spike right there. Same thing with glass and silk, or acrylic and silk. See, this one should give a little bit more. It usually does. The amber likes to hold on to the charge. Well, this one might give a little bit. Yeah, there you go. A much bigger spike there. So as you can see, without even touching the sensor, and me just rubbing these rods, the electric field is reacting. It's getting stronger in places. When it gets stronger somewhere, that means it's getting weaker somewhere else. So it's actually moving that strong charge I created out into the atmosphere to any direction that has less potential. That's Mother Nature. That's entropy. High potential to low potential. That's what all of this is based on. Then a little while later, they came up with a device called the electrophorus. Piece of glass or acrylic. You have a piece of metal with a amber or rubber handle. And this one is, I still don't fully understand this one. So just by me rubbing this down here is creating a static charge on the piece of glass. Now I set that down. Now this has become charged, but for some reason, in order to get the charge off of there to where it's not neutral, once I pick it up, I actually touch it. And then pick it up and put it near it. And we should get maybe a little bit of a reaction. Yeah, a little bit. But this one worked a lot better, the electrophorus, for taking a charge, putting it on something, and then I can set it back down and just do it again and touch it. And do it again and touch something. And add a charge to these things. And that's how they started off kind of playing with electrostatics. Not very effective ways of seeing, visually. There was no sparks at all there. There was no light. There was no sound, nothing. Electricity will disperse in 3 different ways: sound, heat, and noise, or light. Those are the 3 different ways that electricity, when it's discharged and released in a large amount in a very short amount of time, it's going to happen in one of those 3 ways. Now we'll move up to the Van de Graaff generator and kind of take a look at what electric field lines look like. Now this would be considered on a sphere. I don't know how well you can see this. I'm actually going to pull this closer. This one's not as strong. And we'll take a look at, now these are just pieces of tissue paper, and this is a Van de Graaff generator. We're going to turn a wheel. A lot of them are, you can just plug it in and turn a crank. But what I'm going to do is turn this wheel, and you're going to see how electric field lines come off of this surface. It shouldn't take too many cranks, just a few. I mean, that was maybe a total of 4 rotations. And the electric field's way out here already. You can see it's reacting to my hand way up here. And they call that snake charming, when you bend the field lines. But as you can see, it's coming off at a 90-degree angle off of the object, completely perpendicular. They will always come off of it. Now, the interesting thing, you would think if I touch these, right, then the electricity should go down. Conduction happened. But these are insulators. They're not conductors. If I actually touch the ball with the metal thing, boop, and they all fall down. A couple cranks, and right back up. The electric field lines are coming off equally in all directions, falling off at about 1/r². On a point source or a sphere, it acts just like light. It falls off at the inverse square law. Now, here on Earth, that is not what we witness when we measure the electric field. If it were, we would be at, they say it goes up 100 volts per meter. Well, if we were on a sphere or a point source and the electric field acted like that, then it would be 100, 200, 400, 800, 1600, and it would grow exponentially. But that's not what we see. It's nice and linear. And I've noticed that a lot of people get EMF mixed up with EF, the electric field. Now, the electromagnetic field and the electric field are 2 different things. You could say the electric field is part of the electromagnetic field. In an electromagnetic field, you have a current, the direction the electric field is moving, and then you have an oscillating current going around that magnetically. What we have here that we're studying is just the electric field. These are scalar waves. These are not what's the word? Like a radio wave, transverse longitudinal. You know how they show the 2 waves crossing like this, and they say one's electricity, one's magnetism, and there's the 2 different waves. Electrostatics is not like that. Electrostatics is scalar waves. They're uniform. They lie, like as they were coming off of here, it didn't just go out so much in one direction from the source. It came out in all directions equally, evenly. Now this is going to show you how electrostatics changes when you change the radius value of the object it's coming off of. What I did, I don't know if you can see it. I can actually scoot it a lot closer for this one. I'm going to light some incense to make some smoke. I've thought of this one and how to show it. I mean, we can show it blowing out the candle or the fire to even start it. We have a nail here. So what's going to happen is, instead of going out equally in all directions now, it's no longer a perfect sphere or a point source. We have this large, sharp pointed end coming off of it. So what's going to happen is most of the electricity is going to try to get to the tip of this and come off of this. Let me point it down a little bit more. Are they able to see it in chat okay?
Yep.
Okay. We will light it again and blow it out. So the initial, because I don't know if you'll be able to pick up that smoke very well. And as soon as I start cranking, can you tell that it's blowing on it? Let me, oh, don't go out yet. Here, try to do it with the smoke. Yeah, this is one of the harder ones to see. Like I can feel it on my hand. I can feel the air blowing on my hand. They call this ionic wind. They actually say this is where most of the wind, you know, from the upper atmosphere is created by these ionic pulses coming off the sun and other quasars and this and that. And that's how it's nice and uniform in all directions. It's not just from the sun.
Oh yeah, the old ionic quasar wind.
Yeah.
The classic.
I don't know if you're going to be able to see that smoke. No? Can you? No?
Yeah,
Put up.
I think the black will help. Yeah, we can kind of see it. It's very faint though.
Let's see if you notice when I start cranking it, did you see it start going the other way?
No, unfortunately, it's too light to tell.
Here, I'll move it a lot closer and see if we can't get this in here. Maybe if I turn that one off. No. Smoke's a hard one. Oh, a light source. Give me 1 second. I know where a light source is. Okay. I'm gonna have to close this window real quick. How about now?
There you go. Now we can see that electrostatic quasar smoke.
Okay. Might try not to bother it too much. I'm trying to get out of the way. And as I start cranking this, I'll hold it up a little bit more. Yeah, it's blowing the smoke.
Oh yeah, it's ionic winding it right off of there.
Now you can feel this. A lot of people will say, "Oh, it's the smoke particulates that it's doing too, but not the wind around it." And I just think that's silly. I'm sorry. Now you can feel it with just your hand. We've done it at a couple different Flattoberfest, to where, you know, some people feel it more than others. If you have construction hands, you may not feel it as much. But yeah, that's ionic wind. That was one of the first types of electricity that was supposedly discovered. St. Elmo's fire, stuff like that. Natural occurrences, not so much man-made. Now, I didn't really take a look, but what did we see happen to the meter here? Let's take a look at the meter and see what happens when we get a discharge. How do I? Oh, I need to use. I'm touching it like it's a touch screen. I'm used to the Apple iPad. Like, what's going on? Why isn't it clicking into it? Let's see here. Okay. So we got a nice steady baseline again, 65 to 72. And what I'm going to do, we'll charge it up at first and see, is it doing anything to the electric field at this distance? Oh, yeah, we're getting bigger spikes. And we'll see what happens when we there we go. A little bit higher. Move the meter a little bit closer here. Let me pull this off. There's a big one. Uh-oh. Can you hear me?
Yep.
Oh, I just heard something in my ear. I thought I killed something. But as you can see, we got some big ones there. We'll do it again and get some more spikes. Oh, okay. Okay, I'll stop. Sorry. I saw it glitch, the computer. I got to scoot it back. Yeah, 890, couple more in there, probably around 700 or so. You know, the electric field in the area was disturbed greatly by the Van de Graaff generator discharging. It wasn't too bad by it just going off, by me just cranking it. It seemed we're going to have to wait a couple more seconds to let that go down and get the baseline again. And I'll crank it again from a distance. But like I said, this one you don't plug in, it's hand crank. I don't know how much it's affecting. We'll have to see. We'll have to see. Should just take a second here. All right, back to somewhat of a baseline. So I'll crank it. Oh yeah, it definitely went up. Okay. So it seemed like there was that initial spike there. The Van de Graaff generator. And why I'm doing this, because we're going to put this inside of a Faraday cage. And I want you to see what happens. In fact, we'll go ahead and drop this thing down on the ground, this meter, and let it level out. And you'll see it's going to go down now. It will no longer be 70 or 69 to 75 or anything like that. It's going to be much lower. Yeah, I can already see on the graph. It's dropped down and it's holding that steady much lower than it was holding steady there for that last minute. Now this one's the Wimshurst generator. This thing should do a lot more to the electric field. This one actually, it makes ozone. Like it smells like a thunderstorm when I start cranking this thing up. The difference between this and this besides, you know, how the charge is created. This has these two kind of like Leyden jars right here that actually give it some amperage. So it stores some of that electrostatic potential and puts some current behind it. So you can get much stronger jolts when it discharges. They say those go up to about maybe 400,000 volts, which I've been shocked by it a couple times. It's not fun. Oh, it's still at 6130, maybe because that thing was grounded. The table, what if I put it on this? Maybe a piece of styrofoam. Yeah, we'll set it down in here. See what happens. Yeah, I've never seen it stay up there like that at like 60 something the whole time. Last time I did this live, it was down around almost zeroing out and going up to like 6 or 7 volts. Well, this is interesting. Wonder if different times of year are different. But yeah, that's really low to the ground and it's still saying 58 volts to 65 volts. Now I'll pick that up and set it up here. And we should see it go up now. And that minimum should be higher. So we went up to 72 by raising it there. Now it's in an insulator, so it's not touching any. And this device is made to be able to hold it as long as you don't touch the top part. That's where the sensor is. They say it shouldn't affect it, but when you're dealing with small, tiny amounts of voltage like this, me just touching the base of it will. So I'll usually try to set it in something so I can then move that around instead of touching the device. So just by raising it up off the ground in the insulator, because this thing's been touching the ground for the whole time, this wood, I bet it's really close to being the same charge. So there we go, a minimum of 68, high of 73, and then we're gonna put it up on something even a little bit taller. How much taller can I go on there? Here, we'll use the Faraday cage. And now we should see it go up again. And there you go, the baseline is now higher and the peak is definitely higher. We're up to 80. Now, the best place to do this kind of stuff is in the middle of an open field with no trees around. Preferably is, you know, less amount of dirt and things like that. Solid rock would be the best. But every little thing can change it. A tree near you, because that electric field is going to bend around that tree because the tree is grounded. So you really, inside of a house isn't the greatest place to get, you know, real world data or measurements, but this is more just a demonstration of showing that when you raise it up, the baseline goes up and the peaks go up. So our new baseline is 74. And that was raising it 1.5 meters off the ground. But again, we're inside a house with a roof above our heads, all kinds of stuff like that. I'll set it back on the ground to get its baseline. Okay. Now we're going to break out the Faraday cage. So it's
Now, Zach, what
Better-
exactly is a Faraday cage? I heard a lot of people think it's some sort of magical box that makes electrostatics disappear. Like, what exactly is a Faraday cage?
Basically,
a
so you can
Faraday
measure
cage-
gravity, I heard. Yeah.
If I put an object in a
Yeah,
Faraday cage, it'll start to float. From my understanding, is that what happens? It's a magic device. Have you
That's
seen
what a lot of
Indian in the
people are
cupboard?
thinking.
If I put an action figure in there and close the box and open the box, does a little man start playing? Like, is he like enacting out whatever figure he was? Is that what happens?
No,
Okay.
not at all. No.
All right.
So a Faraday cage doesn't even need to be a closed box. It can be chicken wire mesh. It all depends on the size of the wave that you're trying to stop. Like your microwave, if you have one of those, you look at the glass, and if you look real close, you'll see a wire mesh in there with a bunch of little tiny holes so you can see through it. Well, those holes are a particular size. They're made to block the size of the microwave trying to escape that box. So even though you can see through it, it's still blocking those microwaves. Now, you get lower in frequency, the waves get huge. They get enormous. So you can use things like chicken wire and stuff like that to block them out. But no, it's not like an airtight sealed box that's vacuum sealed and this is no. That's not a Faraday cage. You're not
to be
removing
confused
atmosphere.
with the Faraday effect, right, from our GLOBEBUSTERS tech episode. Not to be
Yes,
confused
no.
with that. Something totally
No.
different.
Yeah, Faraday did a lot of stuff. He played with a lot of toys and came up with a lot of different things. So, his name is on all different kinds of stuff. But no, what this does is it blocks EMF waves, electromagnetic frequencies, those ones we were talking about earlier, the radio waves. It'll block. Anything like that, as long as it's got small enough, there's no holes in it to where that radio wave can sneak in there, then it'll block out that completely. But the electric field is, again, scalar. This is different. The electric field is in the air everywhere at all times. There is no place that you find, unless you can leave this place, then possibly there's a place with no electric field. But as far as we know, here, everywhere we've been, there's an electric field here. And it goes down as far as we can go, and it goes up as high as we can go. They actually call it the ionosphere in the heliocentric model, which has to be there because of the way our electric field acts. It acts like it's between two Gaussian surfaces or two capacitor plates. They're a nice place like this, that are about the same size, probably, same length, whatnot. And in between them, we get that gradual 100, 200, 300, 400, 500, 600. And it's not just the air that is a dielectric. Everything. You are a dielectric. I'm a dielectric. All matter. In between these two plates, and they don't even have to be plates, Gaussian surfaces, they call them, which is just something that holds or disperses a charge.
Yeah. And something you pointed out earlier that I'd like to add to that was extremely significant was the way that the gradient of the field, right, it attenuates in the wrong direction for the globular prediction. It gets first of all, it's linear, right, which is a problem. It doesn't have the exponential rate, but it gets stronger as you get closer to the sky instead of closer to the ball, to the ground, right? Huge, massive problem there. Linear field and attenuates in the wrong direction for globularity to substantiate it. And then the second part about the Gaussian surfaces, right? If you look at the definition of a Gaussian surface, you'll see it's like a mathematical construct, right? Like a math tool that's supposed to be an idealized surface that, you can do your calculations with ease without having to how is the electricity going to move through this? You don't have to do any of that. You just assume that it'll just be a perfect conductor, right? And with that though, right, but to replicate that, to actually make that field gradient linear, You have to have two physical objects that are parallel to one another.
Never been done. Ionosphere has never been created in a lab.
Yeah.
Still to this day.
Super
Over 100 years
important.
old. Yeah. But they knew, even Walter Lewin, he expresses that. The guy who came up with the ionosphere. The reason he did was because he knew that there had to be something up there. So they just name it the ionosphere and say it's, these gases that are all plasma now and they're burning at such high potentials and this and that. And it ranges from, what is it, like 400 miles up to 1,200 miles or something like that. Just ridiculous what they,
Think
what
about
they
what
tell us.
think about what they have to be saying, that there's some matter up there. Like as you get higher into the vacuum, right? There's less and less matter. But there's something up there that has a resonant frequency that matches whatever they need to create the boundary layer for the bouncing versus going through the layer. And it's like just real
Resonant
quick
dark matter.
just off the top of your head, real quick, what's the matter that's resonating up there at that frequency? What's it called again? Was it what was it? Oh, you don't even have a name. You don't you just it just is what it is. Okay, cool. Just because ball though, right? Got it.
I love it.
Was resonant dark matter already taken? Because I think that'd be a good one.
Yeah. Northern hemisphere gravitational refraction.
I like that one. Or some northern hemi refracty, or however you want to say it.
All right, so I'm going to show you the inside of the box as well. It has a layer of aluminum foil on the outside and a layer of aluminum foil on the inside. Plus, there's styrofoam going all the way around the outside and a layer of styrofoam on the inside. So it's like super blocking any electric field. We will stand it up. I have it on a piece of styrofoam, an insulator, so actually it's not touching the inside of the cage at all.
I feel like I'm about to watch a trick. Nothing under this sleeve. Okay? Nothing under this sleeve.
Listen, guys, there's no electrostatic gradient in here. Not in this box.
And then we got
then we're
the
gonna
lid.
saw it in half.
Throw that on there and we'll give it a second since I had touched it there. But as you can see, there's still an electric field in there.
Hey, can we make Zack big screen maybe if he's going to be demonstrating stuff? That's probably good.
Yep.
Yeah, I have it just sitting on the ground right now, getting its baseline as close as I can to the ground, and then we're going to lift it up. And if this is some magical box that blocks out the electric field, right? It started with a low field down there, right? So when I lift it up, that low field should stay in there if this is some kind of magical box. So we're going to see what happens here when I pick up the Faraday cage and set it up on the table now. That baseline shouldn't go any higher. Uh-oh. Well, that doesn't make any sense.
What's getting, is it going like what?
No, how am I going to float in a box in a Faraday cage if the electric field went up inside the Faraday cage? That doesn't make any sense. Didn't you say a Faraday cage would allow me to float?
It's supposed to be a magic
That was the
box
claim.
that
I
when
heard.
flat earthers
Yeah.
put things inside of it, everything floats up. That's what I was
But then the
told.
baseline shouldn't go up then, right?
What's
And then the
happening
peak
with
shouldn't
the
go
magic-
up any.
What's wrong with your magic box?
And it's a Faraday cage. I mean, you go to look at, like I said, they have Faraday cages that are chicken wire with holes that are an inch across, open. This has no openings whatsoever. But the electric field inside is the same as the electric field is outside. Now we'll raise it up a little bit more, as much as we can here without, I can move this closer. So I can get it up a little bit higher here. We'll actually turn these on their side.
Why does your electric box gradient keep going up?
I know. It seems like the electric field on the outside of the box is the same as it is on the inside of the box. It doesn't block an electric field, apparently. So can we please stop saying that?
Man, that's crazy.
Are you saying it doesn't block shit?
Well,
Radio
it'll block,
waves.
yeah, the radio waves, stuff like that. It's
Wow,
actually holding the radio waves inside.
that's so crazy, man. Every reference I've ever heard to that is they're like, it's all about magic box and electrostatics. Like, if I put the Faraday
Well,
cage around it, how come it doesn't float? I'm like,
of
I don't
course.
know, because you're misusing it. I don't know.
Well, that whole straw man is based upon us replacing the whole big G force that is working downward with electrostatics as a correspondingly big downward force. But that isn't our argument at all. We're saying electrostatics lightly determines the vector by providing a direction, and then other things like density and buoyancy sort out the gradient and the force with which is applied to bring it down, right? So they're like, oh, you should float when you negate your ridiculous charge or whatever. And it's like, no, even your counter is a ridiculous straw man, right? Is it so antithetical to you guys to understand our position and approach what we're actually arguing? Or is it like, does it hurt?
All of the above.
Now, we're going to show what happens when we have a discharge outside of the electrical field and see how much, remember how big of a spike we would get before? We're going to see if we can get those same big spikes, or if this box is going to help protect it from those discharges. That's the whole idea of, like, you'll have a Faraday cage all over our electronics. They're all, like, if you take apart the dish TV thing, the part that comes into, that you plug into, when you take it apart, that little circuit right there is inside a Faraday cage. That's inside the box. They're all over the place. We use them for all kinds of stuff just to protect really important things so they don't get zapped and there's too much power going through them. So we're going to give this a charge up. And look at that. Faraday cage isn't spiking too much at all. Looks like we had a little one there that went up a little bit. That's probably because I'm just still charging it. Yeah. But nothing enormous. No 800 like we were getting before. We'll even give it a good zap with this one. Hopefully I won't. Kind of scared with that wire hooked up to the computer, but that thing's designed not to have any kind of thing go back the other way. So we'll see, we're going to test it. So this is the Wimshurst generator, the one that makes ozone. Actually, I'll let that one spike. Oh no, we can see it still. All right. So we're going to go ahead and bam, bam, right outside the box. Big booms. Oh, that one went up a bit. Yeah, it's a lot stronger than the Van de Graaff. But still nowhere near the 800 or so we were getting before. Was at 110. Nothing compared to what we were. So it did stop the discharge in the atmosphere around from really getting in there. There was a discharge. It did spike a little bit, but it was a lot more contained and not as violent, to the electronic software inside. That's the whole idea of a Faraday cage. It blocks from, lightning strikes, things like that. It helps when those things happen and that super surge of energy comes flying through the wires. Those Faraday cage helps the really expensive components and parts from being destroyed so easily. But as you can see, they work when it comes to doing that. When it comes to blocking an electric field, not at all. So, that was so annoying. Years ago when I heard that, we've discussed it numerous times, and it seems like you guys are going through all that stuff again. All right. So we're going to set this down on the table here. Now, I had an idea that at the center of Earth could be like a Tesla coil. The way Tesla coils work, the electric field, it makes it a lot stronger, and it amplifies it out this way. Once I get so high above it, the meter goes down to 0 again and starts over. Almost like there's a new electric field starting from this spot. It's wild. But out this way, for, a much further direction, that electric field will go way up more than we've seen it. So I'm going to let it looks like we're almost leveling back out here. Yeah. So 64 to 76 right now. Well, that 76 looks like a big one. We will. Now, I want you to keep an eye on the EMF as well. There's people out there who have said electrostatics don't affect gases, right? Well, here's some gases inside of glass tubes. We have, let me move this over here for you. You can see it better. Whoa. I don't know what I'm looking at now, if you guys can see it. Can you see the Tesla coil?
Well, we were to prove daylight or something?
No, they just say that electrostatics don't affect gases, that it must just be the EMF that is affecting the gases, the electromagnetic field that's lighting things up in the sky. When a Tesla coil, yes, it does put off somewhat of a electromagnetic field right around it. It really energizes the electric field. So I want you to keep an eye on the EMF, the 0.2 right now. It will go up when I turn this on. But nothing is going to happen to the gases until I add voltage to it. And the EMF isn't going to rise that much, but the electric field is going to go insane. So here, I'll click it on, and we're at 0. So you can see the EMF up to 1.9 there. It's probably going to go up a little bit more. Even the electric field spiked for a second. That was just for me turning this on. And this is just a 20-volt DC power supply. Yeah, the voltage goes up to 20 volts. And this Tesla coil can take 50. So it should, like oxygen, doesn't even really want to light up. I should have this spun around the other way so you could see all the gases light up. I'm going to do that real quick for you here. Or I'll just pull these gases up here. And we'll turn the lights off. Okay, so what are we at on the EMF 0.3? Electric field is staying pretty constant, 61 to 70. Okay, I flipped it back on. The EMF should go up a little bit. 2.0 there. 1.9. And as you can see, none of these gases down here are lit up at all. Now, as I add a little bit of voltage to this Tesla coil, whoa, shit. Can you hear me?
Computer lighting up as well. Yeah.
Did the, whoa. It closed
Webcam.
Discord on me.
Webcam froze. Fry your computer?
I don't think so. Let's see.
He's like, do you see it light up? I bet the computer lit up too a little bit.
Let's see. Turn on camera. Come on, baby. Turn on for me.
There we go.
Woo, okay. I'll scoot it back a little bit. Yep. See, this is, yeah, you can mess stuff up with these toys. And we'll share that. Okay. Okay. Computer, be good. Okay, voltage is down. We're going to try and light this thing up without killing the computer again. Whoa, 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 okay. All right, I won't. I'm gonna have to scoot it back even further. I can see it starting to skip. That's
Too many
crazy.
gigawatts, huh?
The danger
Yep.
makes it more exciting, to be honest. The fact that you might get shocked is like, well, this is going to be good.
Okay, so as we turn it, look at the volts per meter now. How high it goes. We're up above 1,000. And that's not even turned up. That's at 9 volts, 8 volts. We'll go up a little bit more. Okay, computer's holding. We got stuff lighting up down there. See the, here you go.
Wow.
There's nitrogen burning. Here is, which one's this one? Oh, this is just air, all of them together. It's more of a purplish hue. I wish I could bring it closer, but you see what happens when we do that.
Don't do that.
Neon lights up the most. It's bright orange, and it'll do it from pretty far away. Oh. Okay. Okay, we're going to turn you down, but as you can see, it went way up there. We're up above 1,000, and it like held it. Do you see that on the graph there?
Yeah.
We were way up, and it didn't come back down. The electric field was super amplified, but the electromagnetic field, it may have doubled a little bit, but it definitely was the electric field lighting up all these gases. Now we can, let me see if there's enough oomph. We'll turn it over this way. Can you see the Van de Graaff generator?
Yep.
From there? And what I'm holding is just a fluorescent ball. We're going to see if we can't get it to light up a little bit. Yeah. Come on. Oh. Let me see here. Now I want to discharge now all of a sudden. Huh. We'll try the bigger one. Ooh, ooh. Okay, I'm scared of this one. I don't think we're seeing it light up anyway, not with the camera that far away. It's hard to get these to do it. They don't put off that electric field nearly as strong as the Tesla coil does. But now we're going to take a look at what happens. Just let that go down. When we reverse the plates. So we have our electric field. And we have our higher potential raining down to the ground from above. And it gets weaker and weaker and weaker until we get to a point where we call it neutral. And we say that's 0. But it's no different than saying that the temperature is 0 degrees when water freezes. There's many more degrees below freezing. So is that really 0? 0 degrees Kelvin maybe. But we took the ground, the charge of the ground, and we named that 0. Even though there's much less charge out there, we can create much, much lower charges. 0 is just, the middle point. So I have 2 pizza trays here. We have, let's turn it that way. There we go. Some pieces of paper that are taped down, and a couple of pieces of just floating paper here. Now this one we'll be able to get closer than we did with the Tesla coil, and I have an idea to make it so you can see it better as well. This is just going to take me a second. I got to change some wires out. The tray set up right. And a lot of this stuff, if you're trying this at home, anything like this, if you're getting them to, your whatever you put in there, if it starts bouncing around up and down, one of your connections could be bad. That'll happen. Through induction, the other plate will become charged if you're just charging one plate, but it's not holding the charge. So the object in between will just start bouncing back and forth real fast. Walter Lewin does great demonstrations on this. Let me, here. Forget I got to straighten these out so they're much further away with no chance of discharge. There we go. We're going to hook the positive up now to the bottom. So the opposite of what we see here on Earth. Oh, come on. There we go. I couldn't find the other alligator clips that I had.
I feel like I'm at a concert and they're about to do my favorite song. Sorry.
All right, now we need a better view. Maybe. Okay, where's the mouse? I'm going to stop sharing this one. Why do I have a circle? Take that back in. Maybe. Okay, there we go. I'm going to close that out. There we go. Okay. I'm going to see what you're seeing there. That's a little too bright. Let me get a dimmer light real quick. That was like the sun. Yeah, this one should be dimmer. And we will be able to move closer here. I need to make it a little bit taller. Oh, you can kind of see. Let's see what we get. I'm seeing a lot of jumping on one of them. So you can see, though, the positive to negative there. They're definitely trying to go up. Let me add. Oh, let me discharge this. Yeah, it must be getting more humid in here. I'm not getting as much of a charge. Plays a huge role. Water is the greatest insulator that we know of. Pure water, which is floating around in the atmosphere all over the place. So the more humid it is, the harder it is to play with electrostatics. Good thing to do in the fall, not so great to do the fall and the winter, not the best to do in the springtime. Here, we'll just take one piece. All right. Sorry about that. Okay. And you can't crank it too fast either. That's one of the things. Keeps bouncing. Ooh, that was a big one. Why are they still standing up? See, they shouldn't be standing up. I got a bad connection somewhere. I'll just... Ooh, there it was. Yep. You got me a little bit. I don't know why it's holding on to a charge like that.
You got me. You got me. I lose. Okay.
Turn it that way a little bit. Get rid of that white light at the bottom. Nope. Still, hold on. Okay, it fell that time. Ooh. Whoops. Dang it. I'm scared to touch it now after that one. Yeah, this thing packs a different punch than the Van de Graaff, this Wimshurst. I couldn't find my other alligator clips. So it's not, I don't know if these connections are all that great up here. Let's see what we get. Oh, it's almost falling over. So the long strands are doing what they're supposed to do, but this little guy, let me change him out. He might be getting... It's weird, even Walter Lewin, say some pieces will, do what they're supposed to do, and some, they like get stuck to the positive. It's weird, like he does a demonstration in that first video where he pours a bunch of confetti on top of the Van de Graaff generator, and when he turns it on, it's all supposed to go flying off. Well, he explains, yeah, in theory, in the mathematical equation, it all goes flying off. But in reality, a lot of it, like he poured a lot of confetti on there. A lot did go flying off, but quite a bit still stuck to the positive. So let's see what we get now.
It's almost like a little bit of random chances in nature, a little bit. It's like,
Mm-hmm. There you go. There's one sticking up there. And down it goes. But yeah, that's... Ooh, whoa, whoa, whoa. That's anti-gravity right there. Where did that other plate go? Oh, okay.
Look at those
If you
gauzy
want to know
surfaces right there.
how I set it up, it's 2 pizza trays with a copper wire going in a big circle loop like this. and then I tape down the edges around it to hold it together. You may say, well, why did you do that? Electrostatics and, mass, density, things like that, kind of go hand in hand. So the bigger, denser something is, the more potential it can hold. The denser it is, the more potential it'll hold. So I added more dense material to the aluminum tray so I could get it to be stronger. We'll try this one more time. You know what? I have some pieces of, I don't want to break any of these glass vials open. Or I don't know if any of the noble gases are dangerous.
Nah, it'll be fine.
Yeah, I'll be all
Just
right.
don't break them though. Yeah.
What's that? One here, one over here. We'll try to get that one somewhat skinny. Okay. Yeah, I wish I had more alligator clips. I thought I had more. I would have ran and got some.
Is this just
Okay.
your electrodynamics room that you have set up to constantly play with the laws of gravity in your house? Or did you set this up for GlobeBusters today? Because this is an awesome
Yeah, no, I
demonstration.
just set this up for GlobeBuster today. Usually this stuff's in my room. The generators are
Really?
sitting in my room. Yeah. Some stuff will be out in the garage. I do a lot of playing out in the garage where there's not as many electronics that I'm scared to destroy. Oh, seems like we need some grease. And there we go. That went right up, didn't it? Discharge it and watch it fall. Why didn't it discharge? Yeah, it's still holding on to it. See that? There we go. You're not getting me again. I ain't falling for that. Oh, got near the edge, the fringe. And see, there's one of those strands. I don't know if you can see it, but it's laying down. It's not standing up. Right here. Whoa. There we go. And then they should fall when I discharge it, but yeah, there they go. So is gravity mass attracting mass, which we can't really demonstrate? I know they say Cavendish, but I've seen physics professor cut apart their Cavendish device because they couldn't get it to work. So isn't science supposed to be repeatable and all that kind of stuff? Anybody can do this right here. I've only seen one other person. I know Austin did this. He used my Van de Graaff generator to do it, but he did it himself. So it's definitely repeatable. Yeah, okay, it's just going to bounce around for a little bit. We're going to discharge it so we don't get shocked too bad. Is it down? Yeah, laying down. Okay. Now, when it comes to gravity, there's something I want to show you guys. Ooh, whoa. And that is, let's see if I can, yeah, here we go. This is from Walter Lewin's lecture. Every time I try to play this, we get struck, so I quit playing it. I went to the transcript, pulled this out. It's word for word, copy paste. And at the very beginning, he's just talking about the nuclear forces. These are the forces that are holding together the protons and the electrons and the neutron. It's holding together the atom, which he'll even admit they don't understand. So if there is such a tremendous force on these protons, well, what is holding them together are the nuclear forces, which we do not fully understand. But thank goodness the nuclear forces are not part of 802. So I will leave that alone for now. So what holds our world together? Would you think that, his answer should be gravity there? Like, if gravity was the cause of holding our world together, he would say, well, gravity holds our world together. But he doesn't. He asks the students the question, so what holds our world together? And then he goes back again and says, on the nuclear scale, 10 to the minus 12 centimeters, very important are the nuclear forces, which right up here he says, which we do not fully understand. On an atomic scale, up to thousands of kilometers, it is really electric forces that hold our world together. So let that sink in. Up to thousands of kilometers, maybe up to the ionosphere. It is electric forces that hold our world together. But on a much larger scale, when we talk about planets and stars and the galaxy, things orbiting each other, it is gravity that holds our world together. And then he even goes on listening to this. And now you may say, that is very inconsistent with what you just told us. Because didn't you tell us that D cancels if you compare gravity with electricity? Yes, but keep in mind that most objects in the universe have only a very small amount of charge per unit mass. So he's talking about in the whole solar system. He says the Earth and Mars have each a charge of about 400,000 coulombs. The gravitational force between them is therefore about 17 orders of magnitude larger than the electric force. So even though our immediate surroundings are dominated by electric forces, including your own body for that matter, the behavior of the universe on a large scale is dictated by gravity. Now, how anybody can say that he is not saying that electricity is holding the Earth together here, I've heard it all. I've heard them all say, I just misunderstand this. If I'm misunderstanding this, please show me where I'm misunderstanding this.
Dude. The classic, you read the direct quote and you're misunderstanding. I'm very familiar with that one. It's a classic gaslight.
Yeah. Yeah, it's like, okay, then point out to me which part I'm not understanding. What part is he saying that gravity is keeping us to the Earth here? Just show me, please. Nobody ever can. So yeah, and this was, MIT, 4 decades. The school that had the most patents come out of it in that amount of time was from MIT, from the students that he was teaching. So I'll take his word for it over somebody here on YouTube. I'm just saying. But yeah, that's gravity in a nutshell. It's controlled by electrostatics. You can play with them. They're all around us at all times. We just saw on the meter. Even me rubbing cat fur and rubber together affected the meter. There is, you can't see it, you can't smell it, you can't hear it, but there's electricity happening here. There's separation.
What I don't like about your explanation, Zack, is that it's coherent, it makes sense, it was replicable, and that it's real. Usually my explanations about gravity are none of those things. I like to wishy-washy just pretend, and then I get to hope a little bit, and then no one knows how to define it or explain it. So now I'm a little confused. If my version of the gravity is thus Insofar as unexplained and 96% dark energy and dark matter, how come your explanatory force seems to be coherent, cohesive, logically backed, and makes sense? Now I'm confused.
Mm-hmm.
Can we use it to
Yeah, and
bend space and time around us, or no? It just doesn't feel right.
This actually, I think, is one of our strongest arguments.
So quick recap, right? Electrostatics are all around, they're everywhere. You rub your hands together, there's all kinds of things going on around you that you can't see. The unseen phenomena, the unobservable without, certain technologies. And it's, as you can see, it's progressed through the years to get more and more advanced so we can play with bigger amounts and make those observations more, observable. 2, Faraday cages do not block the electric field. We witnessed that here live. Put the Faraday cage on the ground, baseline. You lift it up, baseline went up, peaks went up. You raise it up even more, the baseline went up more, peaks went up and more. Just like when it wasn't in the Faraday cage. So just by jumping into a Faraday cage, you're not negating what, heliocentrists like to call gravity, and you're not negating the electric field. We did see, though, that if you discharge something in the air right next to you, it will raise the electric field up around you. The Tesla coil does it. The Van de Graaff did it. Even the little rod with the cat fur raised the electric field a little bit. What the Faraday cage can do is take large disturbances where we're getting over 800 volts, barely went up over 100 volts. So the thing inside the cage was protected from the large discharge, the burst of energy from the discharges we were creating. It wasn't immune to it. We still registered the discharges on the inside. They just weren't as destructive. So even discharges in the atmosphere, are picked up inside a Faraday cage through the electric field. These are made to block radio waves, EMF, not EF. Scalar waves, transverse longitudinal waves, they're different. And then finally, when we reverse the observed phenomena we see here on Earth of high potential above us and a lower potential below us, we actually see the dielectric, the matter in between our two Gaussian surfaces, the plates, actually go up and stick to the low potential, the negative, just like we have here on Earth. We've demonstrated it. It's repeatable. Anyone can do it. I don't understand how, even in the flat Earth community, there's been so much push against this. Now, I think a lot of that has to do with egos of some certain people. Just going to say it. But they're going as far as saying there is no electric field now. That's their argument, because they can't argue against this. They go to the very beginning and say, oh, what electric field? I don't see an electric field. I don't smell it. I can't touch it. It's like, well, you've seen lightning before, right? You know what it takes in order for that to happen. No, you don't? Okay. Well, if you're going to look at it like that, like I can't observe something with my limited human, observation tools, as amazing as they are, I'm not knocking them. I love my eyes, my nose, my ears. They're awesome. My touch. It's I wouldn't give any of them up for anything on Earth. But at the same time, they're very limited. We see a very small percentage of the light spectrum. We hear a very small percentage of the sound being put out there. You know, there's all kinds of stuff going on around us that we can't observe with our human senses. So we need little tools and gadgets. But all these tools and gadgets are the reason that I'm able to talk to you right now. And it's not like, you know, when I hit the button, sometimes it works, sometimes it doesn't. No. When I hit the red button here, it's going to hang up. I guarantee it. When I go to share something, it actually shares what I'm trying to share because all this stuff works. This technology works. This sending of electric signals through things to create stuff is so advanced, it's beyond advanced now. It's crazy compared to this kind of stuff. But that's what all this is based on. These fundamental limitations of physics, of electricity, the field, and magnetism. It's how this place works. So yeah, stop saying things like a Faraday cage is going to stop. You're going to float in a Faraday cage. It's just dumb. Stop it. Think about it for a little bit. Or here's an idea, test it. Let's see, where's that EMF meter? This thing, I think you can pick one up brand new for like 120 bucks. GQ EMF 390. Awesome. The program with it is free. You can get one used. I think I saw one for like 40 bucks. So it's not like these toys are unheard ofly expensive. You know, the most expensive one I have is probably the Van de Graaff, believe it or not. Well, this one was donated to me. I think you can still get them for around 120 bucks. I paid 125 for the Van de Graaff. The Tesla coil was only like maybe 50 bucks. The gases were $6 a piece. So yeah, and I didn't buy them all at the same time in one day. You know, this is 10 years of saving up and getting a toy here and there. But if you really want to know, test it. If you have any doubt, test it. Don't just say no, hand wave dismissal. No, it can't be that. Because I think it's this. Well, that's fine, but hand wave dismissals don't work. All right. To say that there's density and buoyancy without a vector, I'm sorry, that sounds dumb to me. It's like, how does the denser object know which direction to go? It needs that. It needs a direction. It has to have it. Otherwise, nothing would be buoyant. The denser object wouldn't move. It needs a vector. So stop saying that. Stop saying there doesn't need to be a vector. Yes, there does. There has to be a vector. In order to have density and buoyancy, it has to. Period. But yeah, that's gravity in a nutshell. At least how I see it.
Nice. Epic, man. Awesome.
Any questions in chat or anything?
I
Let's
saw a whole
see.
bunch of nuh-uh. Oh,
Yeah, we did have some nuh-uhs, but we did have 2 super chats. One from Liz, who didn't leave a message, but just here to support the channel, support Cami.
Well, thank you, Liz.
Thank you, Liz, the Iron Maiden, much appreciated. And we had one from Roundhound challenging the lads to derive G from Electrostatics. Which,
I can do that.
With Shane,
Yeah.
miraculously. Oh wait, that's what you do for fun, right? Don't you derive G from Electrostatics for fun?
Well, yeah, we
So
have
we'll
the
t-
kinematic
so we'll- so
relationship.
we'll take a
with the
quick look at
dynamic
that.
relationship.
Yeah, let me stop sharing this one. Yeah, I love this. You do this so well.
Well, there's an additional gem, I think, this time because
Now remember, Shane, this lad paid good money for this. gotta give him a good derivation here.
did he wait? Was there a challenge? Was there like a $10,000 bet I should be made aware of, or was
It
it
was-
just for
It was
fun
a
to use?
$5 insult slap in the face to like show that we
okay.
never derive it throughout the episode or whatever. So
All right, let's see. You see that?
all right, what do we got here? We got a big G versus little tiny G.
Right, so little g, right, we're going to get to, but can most aptly be described as this kinematic equation, little a, equals 2h over t squared, which just represents 2 times the height from which an object is dropped, divided by the time it takes for it to hit the ground squared. That is the only application of little, so-called little g that we can call little a, because it's just an acceleration that we can derive on the spot using these two parameters. So surely we can just do this. Right, suppose something was dropped from 20 meters and it took 2.02 seconds to hit. Using this two parameters only, we can derive 9.8 meters a second. We can just go little a from our formula before, which is, starts out over here, but can be reduced to a equals 2 times h over t squared, meaning a equals 2 times 20 over 2.02 squared, which just equals 40 over 4.0804, which is 9.80 meters per second. So we've derived right there without using a dynamic cause for why it's falling. We can kinematically derive the rate at which it falls, right? That's all little a equals. A couple more examples we can go through. Let's say for, a drop from 5 meters takes 1 second to hit the ground, something pretty standard and pretty standard, right? So a equals 2 times 5 over 1.01 squared equals 10 divided by 1.02, which is 9.8 meters per second squared. So why does that work? Well, as our super chatter likely wildly asserted, it's because gravity, right, dummy? Gravity is why that works. Well, we haven't used gravity yet. And if we were to say refute the derivation of said gravity, we could go to our boy Spears over here, Morton F. Spears, put a paper forth, I think, in 2010 called an electrostatic solution for the gravity force and the value of G. And he, through his math over here, used the relationship between Coulomb's law and big G to do, F equals G to, M1 over M2 over R squared, use that relationship to derive an electrostatic nature of the dynamic cause of G, little g. So he's going to come out with 9.8 meters per second, not using gravity or the gravitational force at all. And again, it's going to be based on this relationship instead. Of course, these two formulas are very similar. I would say almost identical. Still have an inverse relationship to the distance with that R squared. The only difference is this is a charge distance and this is mass, right? So if we go back to our Spears paper, quickly going through it, we can definitely put this paper in chat for everyone to go read it. It's not very long, but I think what we have is a snippet of the other one. What he does basically is equate, like I said, gravitational law to Coulomb's law of electrostatics, and through that derivation uses some plugins, comes out to the exact same solution that we do. Let me see over here. Over here, right? So the derivation of the gravitational constant, here are the other ones, comes out in mass per kilogram a second. If we look at over here, Spears came really close. I think it's within 0.2%. And then it's he uses the electrostatic unit. So instead of meters per kilogram squared, we have, I think he has coulomb volt per meter per kilogram squared. I think that's where he came out with it. So he came out with 6.68541 times 10 to the negative 11, and literally using electrostatic forces and summation to derive the gravitational constant, and of course from which we can backwards derive our 9.8 meters per second. So that's a nice quick answer to the super chat, and literally putting math to everything that Zack just put forward with hands-on demonstrations and an excellent showing. So thanks, man.
Thank you so much, Shane. And thank you so much, Roundhound, for that excellent linking the presentation that Zack did to Big G like that, to show that you don't need to assert a causal mechanism of the inherent property of mass is that it has a force that pulls things into it that's proportional to its mass. That's insane.
Right.
So,
not only does that not necessary, we can do it without it, but we can also come up with our own, and it's better, and it's a better dynamic cause. So there's that.
all right, cool. And then we have another super chat coming in from Tony Coriolis, the homie. He says, "Good Prezi, Zack. Much appreciated,
much
Tony.
love,
Thank you
brother.
so much."
That was
Yeah,
epic.
thanks, Tony.
Great.
Yeah, it's been a minute since I busted out the toys and played with them like that. That was fun.
Dude, I had no idea you had all the toys just like behind you chilling that you could just put your camera on and go to Zach's Mad Laboratory with the electric doesn't just start lighting up ionospheres and doing all sorts of electric field tests. We want a Faraday cage? Yeah, I built one a couple years back. Let me just go get it. It's in the garage.
And we can do one on cymatics. here in a couple weeks if you guys want. I got the Rubens
Yes.
tube, the fire
Got
that
it.
shows.
Yes.
Do that scope thing that like reads the frequency into a pattern.
Mhm.
Yeah,
All
it
that.
creates like the it's cool when you play music through it. It'll like certain parts. It looks like an EQ pretty much. Yeah, it's pretty awesome. And then I also built a Chladni plate where you have the plate and you shake it and it creates different patterns. The nodes and antinodes, like you pour sand onto it. And depending on what frequency it is, it'll make different patterns when you hit a resonant frequency. We can play with that one too.
Nice. Yeah, that sounds dope.
Yeah, it's what Tesla said this place is all built on. Frequency and vibration. Key to everything. And I'm still just scratching the surface. I built some of the toys, but you go digging into it and it's a lot like everything nowadays. It's so hard to research stuff. They've hidden so much stuff. Like pulling up EDU papers used to be like the main thing that would pop up when you were searching, something to do with physics. You would at least get on the first page, you would at least get 2 or 3 colleges, Now it's like page 5, you might find a college here or there, but it's all Cora this and blah, 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 blah. Oh, yeah. Research is not what it used to be. It was so much easier back in the day before they started trying to hide everything.
Man, I put that paper in the chat, and only Gleam knows that actually Spears didn't publish that paper that we were referencing. It was published by his daughter. Of course, he had to reference that, dude. That's absolutely correct. I didn't mention it because I didn't think it was relevant, but Gleam mentioned it. Absolutely correct. That is true. He did not publish that paper. His daughter put it out. So thanks and shout out to her. Dude, how does he like? That's just a flex, right? He just showing us that he knows that he already.
He's like, oh, you guys finally discovered how you can derive G from electrostatics. That's cool.
Like you guys finally.
Anyway, did you know that he didn't even publish it? His daughter did. Hilarious.
No, thank you, Gleam. We love you, dude.
Yeah. All right. Well, I think that concludes our episode for this week. Zach, thank you very much. That was an awesome Prezi. What do you got? What do you got coming up this week, sir?
Be over at Iron Rail Media Monday, Wednesday, and Friday morning, bright and early, 5 a.m. Eastern. A lot of fun over there. We get people from all around the plane that'll hop in from time to time. And we rip on NASA, of course, and stuff like that, but it's not like flat Earth centered. It's pretty much, I'd say, more or less like a group therapy for all of us flat earthers that have to, deal with family members or this or that or all the stuff out there that, the way you get treated as a flat earther. And then we also talk politics or we'll talk law. I love the First Amendment. It's one of my favorite things. So we'll talk about that, First Amendment auditor, stuff like that. But yeah, it's fun. It's just 3 old guys sitting around, pretty much griping, like old men sitting on the porch with their shotguns. That would be us if we were all neighbors instead of,
Get off my lawn with a shotgun.
yeah.
Nice.
That's pretty much what it is. But it's a lot of fun. Yeah, we have a good time over there. And then Thursday night we'll have GLOBEBUSTERS Tech. Thank you guys so much. If you guys missed it, Shane and Alan came and hung out with us. And Cami really nerded out. She had so much fun. And she's got so much more to tell you guys. Yeah.
Dude, we learned a lot about polarization. What was the bioresurgence? I think no, that's not the right word. Was it? It was biofringence. Birefringence. Yeah, that's the one. I keep wanting to add bio in there. Birefringence. Yes. Awesome.
Yeah. And it's all natural. These things happen naturally in nature, so applying them to a model isn't unheard of.
Where do you see birefringence in nature? I don't know. When you look at a crystal. Anyway.
Yeah, calcite.
That's awesome. Shane, what do you got coming up this week, sir?
I don't know. Nothing, right?
Well, we actually have a busy week coming up. Monday.
Oh, we have Celestially Theodolite for Jaren coming up. That's Tuesday. Wait, what's Monday?
Monday on Earth Awakenings, we have the follow-up to the celestial theodolite, where we're going to be
Right.
presenting new measurements, all the data that was, in question or whatever that was too in question to use at the time of argumentation, and was anyway. So we got that all hammered out, and suddenly when we verified the data, all the anomalies went away and everything in question dried up.
I
So
love how you present one data point and they go, you can't do that again, and then you replicate it 14 times. Yeah, that's going to be fun. That's gonna
yeah,
be
so we have everything on that with specifics, so we'll be covering that and presenting it. Then on Tuesday, I'll be going over the celestial theodolite with Jaron, former flat earther. You guys all remember him? Good lad. And then what was it? Wednesday, we'll be doing TikTok stuff, perhaps, Shane.
unless we find something better, I think.
Unless literally anything else happens. Unless someone's like, hey, do you want to go outside and throw a baseball? Like, it's anything that comes up, we might do that instead. But if nothing comes up, we're doing TikTok stuff for some reason. And then Thursday, we have something coming up for Thursday.
That isn't more TikTok. We've already gave away our Thursday.
I don't know. It's something. Can't remember what. Then Friday, of course, will be community Twitter night. And then Saturday will be a game show hosted by Andrew. We'll be doing EtherCause trivia. So tune in to that. And I think you can participate if you join the Discord. Check that out.
He usually has I've heard some of the questions he's got for you guys.
He may or may not ask you about tax codes.
Yo, Andrew's trivia is like the hardest questions I've ever been asked ever in my life about anything.
Yeah, he's put a lot of thought into it because you guys are smart. You guys know your stuff. He didn't want to make it too easy for you.
Year-specific tax codes, Zack.
He cracks me up. Yeah, he'll drop by Ironworks in the morning a lot. So don't go listen to any Ironworks over the last 2 weeks because I think he asked some of the questions while they're live.
Nice. Yeah. Awesome. All right. Well, we will see you guys next Sunday. In the meantime, catch up on Zack's show or the EtherCause events throughout the week.